Okay, in today's lecture, I'm going to go into the details about how to perform statistical analysis for data from case control studies. It's a little bit advanced, but still essential. So those are the skills you have to learn about how to perform confounding control by the method of Mentel hands-on methods. Although nowadays it could be done by computer, of course, but if you can do it by your hands once or twice, they're very helpful for you to build up your sense about how it was done. And the other key point is that I'm going to revisit the idea about biases, especially for selection bias and recall bias, which is particularly mostly commonly happen in case control studies. Okay, so I will remind those kind of things. Those are the two key points for today's lecture. So please pay attention. Okay, the outlines. Like what I said, today we are going to focus on the data analysis for case control studies. The Mentel hands-on method has been developed in the very beginning was for case control study only. So it's a modification for the AD over BC. The process we learned for the estimation of odds ratio, right? But also the method has been extended to cohort studies, like what we did for the estimation of rate ratio for cohort studies. And also it's been expanded for many different kinds of the estimation of relative risk. Okay, but let's start with the simplest one, which is the Mentel hands-on method for the purpose of confounding control, like what I suggested. One of the major disadvantages for Mentel hands-on method is that it was developed for categorical variables only. In other words, only if the confounder is a categorical variable. We cannot do it by hands, okay? But now we can do it by computer under the help of the calculus. So don't worry. And the other key point is I'm going to revisit or refine the concept about selection bias, which is a little bit similar but totally different from the idea of confounding. And believe me, you cannot find anything like this, like what I did here in any textbook. So it's very helpful for you to understand the differences between selection bias and confounding. So put them together and then do some comparison. So it will be very helpful for you to understand. Confounding is something, it's an error, it's a bias, we could adjust it. But for selection bias, we have nothing to do with it. You have to clarify the ideas and try to avoid it. Maybe trying to find some other information for you to assess the impact from selection bias if it's not possible to avoid it. Okay? The best policy is to avoid it. If not possible, then you have to figure out how to minimize it. Okay? So it's kind of the process of thinking. It's not something we could adjust. But for confounding, there will be something totally addressable, like what I did for matching, for standardization, right? And for Mentel hands-on methods. Right? There are many skills. That's the thing you are going to learn from the class of epidemiology. And in the end, I'm going to introduce some transformation of typical epi study designs, which will be something between case control study, cohort study, prospective and also retrospective. But don't worry, I'm not going to push it too far. So you just need to have some idea that based on what you've learned for cohort study and case control study, it's possible to mix up or remodify it. Okay, so that's why I started with a very simple concept about cohort study, case control study, prospective, and retrospective. But here it could be mixed up for based on the specific characteristic of the topic or the entity of the disease. So sometimes we need to modify it to save money and time, but still keep the advantage for cohort study, blah, 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 those kind of things. So I'll start with the review on the nested case control study. Nested, not nesty, nested case control study. So it's a case control study hiding or lying within an ongoing cohort or like a parasite. Okay, so it's called nested case control study. So it could take both of the advantage and from cohort study and case control study. Okay, and the other thing is called so-called case-cohort study. It's kind of a combination for case control study and cohort study, right? But actually, it's just a prospective case control study. I'll tell you why and why we need it. In the end, I'm going to introduce a very smart or very useful, actually, for the study design called self-comparison, which is basically a case control study with a perfect matching, okay, before and after. So people are comparing to themselves, okay? So that will be very useful in a very, in some specific situation, it will be very useful and time saving and money saving, of course. So first of all, let me remind you the idea about arts, which is the something developed by Mr. Cornfield, remember, who was a historian. He was not trained as a mathematician or biostatistician or epidemiologist. No, not at all. He studied in history, okay? But he developed some idea which is very succinct and very straightforward for us to estimate the relative risk without knowing the denominator, like what we do for cohort study. So it's very smart. Okay, but first of all, we need to define what is so-called odds, right? Odds is the probability of something happening divided by something not happening. So it's a ratio. So odds is a ratio. P divided by 1 minus P. Okay? And then we did the calculation of two odds to make it odds ratio. So that's why we needed to create another name of it. Or if not, there'll be ratio of the ratio. It'll be even more confusing, right? So he created the idea that odds is P divided by 1 minus P. Like what I said, ratio is just two numbers, A divided by B. But A does not belong or contained by B. Okay, so totally there are two numbers. P is not from 1 minus P, right? If something happening, it's not contained to the situation of something not happening. And the sum of it will be 1, right? It will be either happening or not happening. There's no something like, what's that? Part or what? Even. Okay, so either happening or not happening. Okay, and then we could apply the idea for odds ratio to estimate the relative risk if it's retrospective. What we can have is the total number of people with some disease and the total number of people without the disease. Okay, and this is exposure odds, right? And this exposure odds. Under the assumption of a rare disease is equal to AD over BC. Okay? And also for the prospective view by a core study. In other words, we do have the denominator, A plus B. And A is the number of people who got the disease after a period of follow-up. And C plus D are those people without the exposure, but still there are some people of them got the disease, number C. So it's very straightforward, right? It's the incidence rate for the exposed group divided by incidence rate for non-exposed group. And under the assumption of rare disease, the A is relatively smaller than the sum of A plus B. So A is very small compared to B. So we can ignore it. We can ignore the C too. And then rearrange it AD over BC. Exactly the same. AD over BC, AD over BC. So it's kind of the idea that build out the bridge for the estimation of relative risk, no matter what kind of study design it is. No matter it's a retrospective or prospective, the same. Okay? And both of them are the estimation of the relative risk. Okay, so RR equal to OR equal to RR. Okay, both of them could be called relative risk. Okay. But specifically for case control study, we call it odds ratio. For core study, we call it rate ratio. And the rate here could be cumulative incidence or incidence density. Remember? Okay, but cumulative incidence got no unit, so the ratio no unit. Right? But if you are performing the calculation by incidence density, which got an unit, right? But still eliminated because unit, so it's just, you could eliminate it at both sides. So no unit again, because it's a ratio, no unit. Okay, it's just a review. So it's better to keep it in mind. It's very, very important for the comparison. The cases are representative for the ones with the disease in the population, of course. And the control should be representative again. But how? How are we going to make them representative to the case group and the group without disease? Random sampling, right? And the process to get a random sample is so-called random process. That should be something given by Andre and emphasized in my previous fundamental courses, remember? Don't worry too much about the disease has to be rare. People might ask how rare is so-called rare. But not so rare is fine. Even if it's as high as 20 or 30%, that's fine. It has been proven by the unbiased estimation by many outstanding biostatisticians. Okay, so don't worry. It's not very important. But all the textbooks are saying it. I cannot ignore it, right? But in the very beginning, the idea is that it has to be rare. But eventually we prove it. It doesn't have to be very rare. Okay? So that's the exercise for odds ratio calculation. So the OR here just give you the hint that the study design is a typical case control study, right? Okay? But this is a typical 2x2 table again. But how are we going to do the calculation for odds ratio? But first of all, you need to identify what is A, what is B, what is C, what is D here, right? So you might need to rearrange it in this format, because A means the number of people who exposed to something and also got the disease. So disease exposure, so this number, right? So this is actually A, right? And B will be the people without the disease but exposed. The one with cancer, without cancer, right? But he or she was a smoker. So that's the number without the disease but smoking. So B will be 233, right? And rearrange everything and put into the 2x2 table. Please make sure that you remember to rearrange them. To make sure this is A, is that A, B is the B, C is C, and AD over BC. Okay. We call it a crude estimation. In other words, we are not considering any other potential confounders at this stage. And generally, that's the first thing we are going to do. We call it univariable analysis. We only care about the exposure of something, the effect of exposure to the relative risk of the disease. Now, if you put it in the right way, then you could get the right number. Even if you don't, if you put the correct number, you'll get most of the score in the final exam. I'm not teaching English or math here, right? I'm teaching epidemiology. So the correct concept will be the most important thing. Okay, so if you do it right for the arrangement for the position of A, B, C, and D, it will be very easy, right? A times D, which is 341 times 643 divided by 233 times 421. So the answer will be 2.24. In other words, for the people who are exposed to something, the relative risk is more than 2-folds, okay, or 100% higher, 1.2% higher, 120% higher for the risk. So if the number is less than 1, then exposure could be preventive, like vaccination, right? Okay, so now it's just double the risk compared to one who are not exposed to it. Okay? So this has been, you should be pretty familiar with the whole process here. But if you do it with the computer, it will also give you a 95% confidence interval. So if it's available, please report it in your thesis or report. Okay? But here, they just do it with the unbiased estimation again. By the variance or standard deviation thing, plus minus 1.96, remember? That's what you learned in biostatistics, right? But computer will do it for you. So it'll be something like maybe 1.36 to 3.54, and the p-value will be less than 0.05 because it's pretty high. And the numbers are pretty high, I mean the total number, so it'll be mostly significant. Okay, but now how are we going to use the method called the Mantel-Hansel method to deal with it for confounding control? It's been developed in 1959. In other words, before 1959, we have no way to deal with it. Before that, the only two available tools would be standardization and live table. Okay, but we have no way to deal with the other factors, which is a categorical variable, before 1959. And Mentell-Hensel are just simply the less than of two biostatisticians. Okay, so here is the reference. For cohort study, the risk or the rate of the exposed group divided by the rate of non-exposed group. So that's the relative risk or the impact from the, or influence from the exposure, right? And this could be rearranged by this. A times C plus D divided by C times A plus B. Okay, R equal to that equal to this. And we just rearrange it like what it did for AD over BC. These two will be moved to the bottom as the denominator. And the two who are apart from each other will take to the top as the numerator. Now that's math. For case control study, it's AD over BC, right? Now that's the same. The closer one could be removed to the bottom, and the apart ones put to the top. So they are the numerator and denominator. Those are the estimation of the crude rate ratios. Okay, and here's the formula for Mentell-Hensel method, and it will give us a pooled or summed or adjusted estimation of odds ratio. So let's start with the observation here. It's still AD over BC, right? But it's something new here. That's the number of the total number of each stratum or each 2x2 table. For example, for this, if we stratify by gender, then we'll create two 2x2 table, right? If we have, what's the total? Maybe 1,500 male and female. And maybe we have 1,000 male and 500 female. Okay, so that'll be two strata there. If we stratify the table, 2x2 table by gender, we'll have two, right? So here I will be 1 or 2, male or female. And we add it up. Do the sum at top for numerator, and also do the sum for the denominator. Well, that's pretty straightforward, right? Intuitively, it sounds right, but biostatisticians has proved that it's an unbiased estimation again. Okay, it'll be the same thing for the cohort study. It's the same as A times C plus D here, and C times A plus B here, and divided by the total number of each stratum. If there are two stratum, one for male, one for female, then that's the number of male plus the number of female. Number of male plus number of female. This is summation, right? And smart ones might ask me, what is the C for? Or another one joined the team, okay? It's Cochrane or something. So Cochrane, Mentell-Hensel. But it's based on the idea developed by Mentell-Hensel in 1950s. So here's the information you are going to see if you want to perform a confounding control by the Mentell-Hensel method. So basically this is exposure obese and non-obese, right? Exposure status. And CVD, cardiovascular disease, non-cardiovascular disease. Okay, and stratified by age. Okay, age younger than 50, equal or older than 50. So in other words, with this kind of data, we'll be able to adjust for age as a confounder, because that's the variable used to classify or categorize them. Okay, it's because it's a categorical variable, right? So we could split them into the two 2x2 tables. Okay, and people might ask, Since we have two 2x2 tables, why don't we just do the AD over BC here? For odds ratio younger than 50, you will get 1.48. And the other one, AD over BC, you will get 1.54. 1.54, sorry, and 1.58. But if you do that, it did not summarize them, right? That's one thing. And the other thing is that this is so-called stratified analysis. You are not adjusting it. So it's a totally different story. With such kind of split calculation for odds ratio is trying to identify the interaction or effect modifier. But it's about the same, 1.48, 1.54. It's about 50% higher, right? So no matter for people younger than 50 or older than 50, the effect of obesity is about the same, or about the same, about 50% higher. Right? In other words, the effect of obesity does not modify by age, right? So it's about the same. But it's not that story. We're not trying to examine or test or detect interaction. We are doing the adjustment for age structure. So that's why we need to use the Mantel-Haenszel method to summarize the odds ratio estimated into one number, a single relative risk indicator. Okay, so please use the formula on this page to do the estimation. Because it's odds ratio, so it's AD over BC, right? And weighted by the number, total number of this and this. Okay, add it up on the top, add up on the bottom, and then calculate it. AD is always on the top, BC is always on the bottom. Okay, and this is the sum of 1, 2, 2x2 tables. Here, 1 and 2x2 table 1, 2x2 table 2. And the factor which is used for the stratification will be the confounder considered in the scenario. A kind of extension of AD over BC, right? I'll just split it up. Okay, 2 minutes. So without the consideration about age, we could just put them together. Time plus 34, that's 46. And 90 plus 164 is B, 254. So without the consideration of age, this is so-called a crude estimation of odds ratio. Crude odds ratio, which is 1.93. But age could be a potential confounder, right? So if we do the adjustment by Mantel-Haenszel method, what is the number you got? 1.52, 1.5 something. But this is the crude one. It's about 2. But if you adjust by Mantel-Haenszel method, it's 1.53. So it's overestimated because of the confounding effect from age. So it's worthwhile to do it, right? To adjust it as a confounder for age structure. Okay? Yeah, it's kind of a little bit rough to put them just 50 or over 50. You could do it from 30, 40, 50, 60, 70, 80, 90, blah, blah, blah. Right? In 10-year age band, there'll be a more precise adjustment for age structure. Right? So this is just an example. I know it's pretty rough. That's the one without the consideration about age. So I just simply add it up. So we call it crude one. Okay, but we need to use the formula suggested or developed by Mantel-Haenszel to do the adjusted one. So I'm going to show you how to do that. I'll just simply use the formula. This is another story. This is not adjusting. This is used to identify interaction or effect modifier. This is not what we are supposed to do. Okay? We are not detecting interaction or effect modification here. We are trying to adjust it as a potential confounder. They are totally different scenarios. This is not adjusting. This is just showing the fact that for the people younger than 50, for the people older than 50, it's about the same. So the effect of obesity doesn't change because of the age, right? That's the conclusion. Now let's do it for the pooled odds ratio estimation, or sometimes we call it adjusted the adjusted OR. Okay? So N1 here will be 600 from this 2x2 table. N2 here is 400. 400 is AD of VC, AD of VC from table 1, 2x2 table 1, 2x2 table 2. Okay, but still AD over VC, AD over VC with the total number of each 2x2 table as the weighting. You got 1.52. Okay, so if we don't do anything, even ignore anything about age, it's 1.93. After the adjustment, 1.52. Which one do we prefer? Of course, this one, right? Okay, so 1.52. So in other words, the effect of the obesity is just increased risk of about 50%, not almost double there. Okay, does it make sense? Are we understanding each other? Okay. Okay, what about this? Exact the same information, but here I'm talking about pooled rate ratio. So it's kind of a hint that this is a cohort study, right? So you just need to apply different formula developed by Cochrane, Mantel, Hensel, like what I show here. This is the formula we are going to use. The answer would be 1.44. But if you do like what I did here, I'll just add it up and do the calculation of crude rate ratio will be 1.79 or about 1.8. So it'd be 1.8, 1.44. So again, it's overestimated if we don't adjust for age structure. Okay, so exact the same data, we could do different kind of things. Why is that? Because of study design. Here is a core study now. Okay, so it's a cumulative incidence, right? Okay, and I can tell you that there's a similar formula developed by other people, other biostatisticians, if the data is incidence density. But both of them are about cohort studies. Of course, we could do exactly the same thing separately, but it's not answering the question, right? It's an estimation of the rate ratio for the people younger than 50 and for the people equal or older than 50. They will get two different estimations of rate ratio. But it's checking the idea that if the effect of obesity could be modified by age. Right? So we're asking different questions by different hypotheses. But here I'm asking you the effect of we are trying to estimate the effect of obesity to the risk of cardiovascular disease by adjusting the age as a potential confounder. Okay, so it's 1.44. A little bit different from what you can find in case control studies. But this is the correct one because of study design, we need to modify the estimation a little bit. So the other thing is that, is it possible that we could control more than one categorical variable by Mantel-Hensel method? The answer is yes. This is what I said that in the previous example, we just split them in two age groups, younger than 50, older than 50, right? But what if we do it in a more subtle way or more detailed way? 15 years, 5 years, in a smaller age band anyway. Is it better? Yes. The issue is that we need to have a huge or much bigger sample size to make sure that there's no zero in it. Right? If it's AD over BC, if there's something here 0, then we fail to do the estimation. Will be if there's any 0 here, that will be make it 0 infinite, right? So that's assume that we have a huge sample size. Then it doesn't matter too much if we split them into many different 2x2 tables, right? So that's the ideas of the modeling. Calculus, we're going to do it by computer, okay? And also we could split them into 2 if we don't care if the sample size is big enough or sufficiently huge. We could even split them into gender, male, female, male, female, male, female, male, female. And then we have more than 1, 2, 3, 4, 5, 6. Then we have 12 2x2 table, right? We could do exactly the same thing. Okay, 12 add up, 12 add up, and then we could adjust it. Then we could adjust age and gender, right? Okay, and again, let's assume we have a huge sample size. We could split them into ethnicities, socioeconomic status, blah, blah, blah. So that's the idea of multivariable analysis by modeling, right? So this is expansion. To that stage, we don't need to worry about is it categorical or not. If we chop it in a very fine, with a very fine unit, that will be exactly the same as the estimation for confounders, and which are continuous variables. Okay? So that's the extension of the idea of Mantel-Hansel method. Again, it's been proven that it's unbiased estimation, so it's perfectly fine to do that. Okay, so that's exactly the way we do it with the modeling method. Okay, so Mantel-Hansel method is a foundation for confounding control, which is only usable or applicable for categorical variables. But for continuous variables, we feel comfortable to use the modeling method to do the estimation. Okay, so let's move on to something more exciting, selection bias. Okay, a lot of people think that selection bias is easy. If the exposure or the outcome is selective, then it's selection bias. No, not at all. Not that straightforward. Okay, a selective exposure or selective outcome not necessarily leading to selection bias. Okay, why? You need to pay more attention about, talk about case control study first. That's fixed to the thinking about case control study. If the case is selective, or could be hospital, single or mono hospital study, then the cases there might be very different from everyone else with the disease in the population. But it only caused the limitation of generalizability. So in other words, the estimation result might not be generalizable to a bigger scope of the population or national population. But if the issue is selective controls, in other words, the controls were selected by some reason, then it will cause invalid estimation of relative risk, which is more likely to be selection bias. So that's why I emphasize the idea that the selection of control, which is representative and non-selective, will be even more important than selecting representative cases, because it will be more likely to have selection bias from the control side. And recall bias is the other thing. It's a kind of information bias. It's just simply that the information from the case and control might be different because of disease status, which is quite normal and pretty intuitive, right? The ones without disease might ignore or they don't care about the exposure. But the ones with disease, especially for serious disease, they might blame themselves, blame everybody, blame anything, and they might exaggerate exposure, right? So it's very likely that the information given by case and control could be different, right? But the problem is the recall bias is difficult, increase the difficulties in assessing the direction and extent of bias. It could be differential or non-differential. So once it happens, it will be pretty hard to deal with. Differential means non-random, and non-differential means random. The only way, or a better way to deal with it is to try to elaborate it by other existing records, like electronic health records, The acronym will be NHRS. If we have record, then we could double check to see if there's a possibility of recall bias. Without other sources of database, it will be very difficult to assess the direction and also the extent of recall bias, no matter it's differential or non-differential. But selection bias, if you just Google it, selection bias, you could find more than 1 million definitions about it. And here's a typical one. But this is not a casual one. This is cited from a booklet called A Dictionary of Epidemiology, published by Oxford Press. This is not a regular publication company, right? They do it in a very careful way. And here's the definition. Distortion that results from procedures used to select subjects and from factors that influence participation in the study. A little bit vague. It does not make much sense to me. Yeah, so I tried to find another one. Error introduced when the study population does not represent the target population might be a little bit correct for control, but not for case. What about cohort studies? Okay, so these two might not be so satisfying to me. Okay, but the other definition is that the selection bias occurs at the stage of recruitment of participants, especially for case control study or retrospective studies. So if something happened, of course it's about procedure, but here emphasize that it could happen at the stage of recruitment of participants, or it could happen during the process of retaining them in the study, especially for cohort studies. So this is a better definition because slip up for different kind of scenario. For case control study or retrospective fashion, it could be selection bias will be mostly likely happened at the stage of recruitment, okay, especially for controls, right? And if it's a prospective fashion or it's a core study, then it's more likely that it's happened at the process of people who stays till the end of follow-up. Okay, so this makes more sense to me, and hopefully it will make more sense for you comparing to the previous two definitions, right? So in core studies, the most likely way to have selection bias is selective loss to follow-up. Or we could say it's the retention of subject maybe differentially relating to exposure and outcome. It has to be related to the exposure and also about the outcome. In other words, the people exposed to something, they are more likely to stay or they are more likely to lose, run away. And also the exposure is related to the outcome we are interested in our research. There is a perfect storm, okay, for core study. And that's generally the way of the occurrence of selection bias. Okay? And a great example is the healthy worker effect. In core study, generally we follow up a group of people with a spatial exposure, right? And compare it to the general population. Remember? They could do the adjustment of confounders by standardization or matching, blah, blah, blah. But in some cases, we find that theoretically or in our hypothesis, we assume that the exposure is harmful to health. Okay? So they are supposed to get higher risk of illness because of exposure. Maybe it's the information from animal model or from other observational studies, blah, 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 or even from randomized control trial. We believe something is fatal, not fatal, but it could be risky to cause people, to lead people to get disease. So something terrible. But in different kind of occupation or different industry, we may find that it's not so harmful or even protective. That's weird. They're potentially exposed to something, but we cannot observe the same or even different direction, opposite direction of relative risk. It's a special type of selection bias that occurs in core study of occupation exposures when the general population is used as a comparison group. Why is that? The best example is firefighters. Yeah. And they're healthier and stronger and they keep on training and to keep their body shape, right? Yeah? So the risk for example, cardiovascular disease, of course, will be lower. So that has been selectively to expose to something, right? And the reason why they were selected to have the occupation is because they are stronger, they are healthier, and that's directly related to the outcome, right, or the risk of disease. So healthy worker effect is a great example for selection bias. So in a prospective cohort study, selection bias has to be related to both exposure and outcome. That's what I have emphasized before. And the factor affecting the enrollment of subjects would not be expected to introduce selection bias in a prospective fashion. Why? Since the study subjects are enrolled before they have experienced the outcome of interest, so it could not be selected in that way. And the outcome hasn't yet occurred, okay? But don't worry too much. This is a little bit advanced. You just need to know that it could be very complicated for the perspective. If it's a prospective study, it's not so straightforward because when they are exposed to something, the outcome hasn't occurred yet. It's a little bit philosophy, right? But if it's a retrospective cohort study, it'll be something more available when you're doing the research with the existing data set, like national health insurance. The selection of choice of the exposed or unexposed group had been related to the outcome of interest in hypothesis, right? That's why we perform a study. And the second part is that since the retrospective cohort study starts after all cases of disease have occurred, subjects generally would know their exposure and outcome status. Okay, so that's the reason why that the selection of the case and control could be selective and could be related to the reason why they become a case, right? So in the retrospective cohort study, that's the reason, potential reason why it's more vulnerable to selection bias. Just think about it, read it for several times, think about it, but don't worry too much. Okay? For selection bias in case control study, you have already known that, right? Selective control are even worse than selective cases. And any reason for the differential surveillance, referral, or diagnosis subject in cases, all of them are more about generalizability, not really lead to selection bias. So we have to pay more attention in the process of choosing controls rather than choosing cases. So the selection bias will be more likely to happen in the situation that low response or participation rates if the likelihood of responding or participating is related to the both exposure and outcome. Outcome is the disease status, right? And exposure, if it's related, if it's the reason for being selective, then it's it's a perfect storm for selection bias. Example, sick people with specific exposure are generally more willing to join research as subjects, especially if they join the study, they could get a free treatment with a new method, for example. They might exaggerate it a little bit. Then that's a source of selection bias. But it's more about the practical issues when you are trying to perform a research. Generally, it's not possible to be tested in any exam, right? But when you are judging the quality of the research outcome, then you need to have some idea about selection bias. Let's give a brief review about confounding. What is confounding? Professor Rothman is my idol, and he defined it in the textbook, one of the recommended textbook. He defined confounding as the confusion or mixing of effects. The effects of the exposure is mixed together with the effect of another variable, leading to bias. Although he's my idol, but this is not satisfying to me. Again, first of all, confounding or confounders mean in Latin. Have you ever learned Latin? The ancient European language. Yeah, it's confoundir or something. But it means mixed together. Okay, but it's not just mixing, or at least it's not evenly mixed. It's not the idea of evenly mixing. So that's to go to ask another master in epidemiology, and he says confounding is the distortion of association assessment Generally, we do it with estimation of what? Relative risk, right? Caused by a well-characterized independent third-party factor. Remember the story about your cousin when you are getting married, which inequalize the comparison groups. That's confounding. Okay, it's a third factor which is very important. And the distribution of that, the specific exposure, is very different in the two comparison groups. It could be exposed, non-exposed group, or case and control group. So in core studies like that, and case control study like this. Okay, so we need to deal with it to make sure that the comparison groups are comparable to each other. Or we could say that we have to ensure the comparability between the comparison groups. Okay, so it's uneven mixing, not like what Professor Rothman say. Yeah, he's alive. He's working in Oxford, I think, now. So here's the table. It's top secret. It's not available in any textbook or anything on internet. So even if you want to Google it, it's not available, okay? But believe me, this will be very helpful for you to discriminate selection bias and confounding, okay? First of all, the entity about selection bias is the difference between the study subjects and the target population, okay? The study sample you have is different from the target population, where you are going to generate your study results to. There's a gap there. But for confounding, it's the difference between the comparison group. It's happening within your study. So that's why we could do some adjustment if it's available. I mean, if you measure age, you can adjust for age. You have gender, you can adjust for gender. Okay? You could either do matching or could do modeling or standardization, blah, blah. You have many, many ways to do it. So you have many tricks to play to deal with confounding. But for selection bias, it's very unlikely or it's not easy to do anything to deal with it. So the best policy is to avoid it or try to get further information to assess the impact from the selection bias. Okay. And directional bias, again, is very hard to assess again. We have no idea if it's exaggerated or make the outcome shifting to none at all. Confounding, it really depends. It depends on the way you do the measurement and the way you do the adjustment. Okay, so it really depends. Okay, but it's not true that the more we control confounders, the more precise the estimation will be. Not necessarily true. It's kind of art. Only if you do it appropriately, okay, then you could get a better one. If you don't incompletely or push it too much, you control too many confounders, generally it just create artificial confounding by yourself. So it's not necessarily better. It's a kind of art to find the best way to do it appropriately. Okay, so this table is very important and very useful for you to discriminate the different kind of bias. Confounding is a bias, and selection bias is the other one. But they are different. The different level, it happens at different level, at different stage. The entity is different. Selection bias is the difference between the study sample you have in your hands to the target population, the population you are going to generate your research results to. But confounding is the difference between the comparison group in your research. So it's happening in your research. Okay? So it's possible to deal with it by many, many different kind of ways, matching, modeling, or standardization, blah, blah, blah. But for selection bias, it's very difficult to do anything to deal with it. It's either not easy or not possible, not even possible to do it. And also the direction of bias is very hard to predict for selection bias because we have no idea who's not coming or who left. They don't tell you why. They just disappeared for core study. Okay? And the control, they just come for potential reasons they don't want to tell you, right? So it's very hard to deal with or to predict the direction of bias. But for confounding, it's possible. It's not the case that the more confounders you consider, it will be definitely to give you a better answer. Not true. The key point is to do it appropriately. Don't too much, not too much, or not too less. Okay, so this is very helpful for you to understand. These two phenomena, they're all biased. Okay, Give you a brief review for nested case control study again. It's a modified study design that could take both the advantage from case control study and cohort study. So it's generally nested in a cohort. So it's constructed by the cases detected in the cohort and the control randomly selected in cohort 2. Because it's ongoing cohort, right? After a certain period of follow-up, we'll be able to identify people got the disease and people were still healthy. And we just take every single one who got the disease and compare it to a random sample. That's generally the way we do it for a nested case control study. We simply collect a sample for exposure assessment before the onset of disease. So at the baseline of when you're recruiting the cohort members, you could do a lot of measurements, right? Like a questionnaire or do some body measurement, like blood pressure. And also you could keep the medical sample, like blood, urine, or tissue, something like that. Although it might be difficult, before the onset of disease. So this is what a typical cohort study all about, right? And also you could do the matching. If you have some people who got the disease, you could choose the ones from the random sample who are having no disease. They could perform matching. It's exactly the same as what we can do for case control study. For the purpose of what? Confounding control, right? And if they have been matched, we call them in the same risk set. So the cases of control, they are at risk for at the same time, but they have exactly the same age or gender and blah, blah, blah for the confounders we are going to control. But if you perform matching, again, you need to use more sophisticated statistical method like conditional logistic regression. If you take the course for quantitative research method next semester, you are going to learn it. It's just a small twist to logistic regression, so it's pretty easy again. But that's the way we have to do it to estimate the odds ratio because it's typically a case control study. But please pay attention that the cases before onset could be possible a control. So for the cases for this study, it could be a control for the other nested case control study. That's fine. The advantage is about timing because temporal relationship is the only essential or necessary one for the judgment of causal relationship, remember? Okay, and because the nested case control study is a study nested in ongoing cohort, so we are pretty sure that the exposure happened before the onset of disease. So you could hold the temporal relation. And you have no need to follow up exposed for the whole cohort members. You just need to focus on the cases, which it might be tiny or small part of it, and another random sample as control. So there's no recall bias because we are pretty sure that we have the records about the exposure status in the very beginning and then follow up to the end. And so the cost will be lower, especially for lab work, because you don't need to do it for every single one. In the past, the examination of the SNPs for the DNA in the blood sample or the swab of your oral cells could be very expensive. Although it's a little bit cheaper now, but it could be still $30 or $40 per person, still expensive. But for nested case control study, you just need to do the examination for DNA for cases and a small portion of the controls. You don't need to do it for every single one to save money and efforts. And the statistical power is independent from the size of the whole cohort. It's only dependent on the cases and the selected random controls. So even if the original, the ongoing cohort is not too big, it's fine. So that's the nested case control study. And do remember the advantage about it. But basically, you could take the advantage from both from case control study and cohort study. Save time and money, but still hold the temporal relationship. Okay, and the next one is so-called the Case-cohort Study. That's a little bit confusing, right? But I can tell you that it's just simply a prospective case control study. It's a modified study design of cohort study without exposure measurement of the whole cohort. I'm going to show you the figure. It will be very helpful for you to understand what's going on. A typical case-cohort study is constructed with the cases detected in a cohort and randomly selected sub-cohort members. See? Almost exact the same like a nested case control study. We just call it the control ones as a sub-cohort. Okay. And everything will be exactly the same. The only difference is a prospective case control study. So we call it a case-cohort study. The exposure assessment is done for cases and control only, so it's cost-effective, like exact the same as the nested case control study. And it must be able to access any member of non-subcohort to collect information on the ones who become cases. Okay, so because the ongoing cohort, and you have to make sure that you could access to every single one. Then you just simply collect the information from the cases with the disease and the subcohort. If you cannot access to every single one, then you cannot get the extra information you need. Okay, and also you need to adopt a spatial statistical method. It's a modified survival analysis, which will be survival analysis will be covered in a quantitative research method in the next semester. So what we can get is incidence rate. So that's very important. So it's something similar to case control study, but we could get the rate. Then we could estimate the rate ratio or hazard ratio. That's something not possible for case control study. Okay, the previous study is a little bit complicated, but for the figure it's very straightforward. Here's the whole cohort. We established a cohort, so they qualify to be a cohort members. And we follow up for a period of time, and some of them got the disease. Okay, so then they've been involved in the final analysis. And also then we could choose a randomly selected subcohort. Then we do detailed estimation for their exposure, but they don't have disease, right? And involve the analysis. And for the non-subcohort, we don't care about them. We don't need to measure anything of them. We just need to access every single one. So we could do everything for the estimation of the exposure for cases and the selected subcohort to save time and money. Okay, so here's an example, and actually this is my dissertation almost 20 years ago. Okay, it's a full cohort for about 1/4 million population in Shanghai, in China. Then we do age stratified randomly selected subcohorts, and some of them got the disease here, which is liver cancer. Right? And then in a group of non-subcohort, of course, there are some liver cancer cases. So 8 from here, 350 from there. So the total will be 360. Okay? And the ones who are not the subcohort and no disease, they will be excluded from the analysis. And we only need to do the comparison of the subcohort from here and the cases from the whole cohort. Let's do the comparison by a modified Cox regression. Okay. The advantage is that we could hold the timing issue to satisfy temporal relationship in causality, and we could increase the statistical efficiency because we have the issue about timing, right? Rather than nested case control studies, everything is retrospective. Now we get extra information about timing, so we have more statistical power to identify the differences. It's applicable for multiple outcomes. So actually that was a study covering all the cancers, and my part is about liver cancer. You could do it for breast cancer, lung cancer, blah, blah. It's all the same setting. So that's the advantage for cohort study, remember? And also that's something not possibly done by a case control study, is that we could even do a time-dependent exposures, because we'll go into the details about all the occupation history of every single female workers in textile industry in Shanghai. So it's possible to perform such kind of time-dependent variables. In other words, we could take care of the issue that the exposure change over time. People change their job, right? And the process of production might change over time again, right? So the nature of the data is time dependent or changed by time. So it can be taken care of by this kind of study design, and not possible for any other kind of study design. Okay, the last one is also a modification of a case control study, but it's a very smart design. We call it self-comparison. Let's start with an example published in New England Journal of Medicine, one of the top journals in the field of medicine. The title is The Triggering of Acute Myocardial Infarction by Heavy Physical Exertion. We call it Weekend Warrior, right? Some people, they don't do anything, they just on weekdays and do a lot of research, a lot of physical exercise during the weekend. Is that helpful? No, not necessarily true. Okay, the background is that the effect of heavy physical exertion to the onset of AMI, heart attack, could be very short, making it hard to select a comparison control group. That's the background. The exposure to the outcome is so short, so it's very hard to find an appropriate control group to compare with. Okay, so this is also called a case crossover study design. The cases simply compare to themselves before the event, or AMI here, or heart attack. And it's perfect matching. So you are only one week older than you, right? Exact the same for gender, for most of the cases, sorry. Exact the same for genetic background, socioeconomic status. It's all the same. The only difference may be the short-term exposure right before the onset of the disease, like heart attack. The control exposure period is just, it could be the annual frequency of physical activity. It could be done by records or questionnaire. And the case exposure period, we could identify the time, the type, and intensity of physical exertion in the day before the onset of AMI, right? So if you do it precisely, you could do similar thing for the control periods to assess the very short period of time of the exposure to be effective. Okay. And results, about 4.4% of people reported heavy exertion within 1 hour before the onset, the cases. And the relative risk for heavy exertion within 1 hour before the onset is 5.9. And you could find a dose-response effect for less habitual physical activities. For the ones who don't really do a lot of examination, you could find a dose-response effect like what we observe here. So if you don't do it too much every single day, then it's more likely to happen for you if you have very strong or very intense exercise before. And the induction time for heavy exertion to the onset of AMI was less than 1 hour. So this is exactly the story, like what I said in the background, right? Okay. And the other example is another study also published in New England Journal of Medicine. So back to the 1990s, this is a very hot topic, it's a very useful study design to perform such kind of study. This is a very interesting and also important public health issue. Association between cellular telephone calls and motorcycle collisions, traffic accidents, in relation to the mobile phone use. The hypothesis is that whether using a cellular telephone while driving increased the risk of motor vehicle collision. When I went to UK, people don't understand what is so-called cellular phone. And eventually I found it's a mobile phone there. Anyway, it's just mobile phone. The brief exposure caused a transient change of risk of a rare onset disease event. So if you hand it up and it's back to normal, and it rings, the risk should drop a lot, right? So it's a typical or perfect situation like what I said before as the background. So this is definitely what is supposed to be used for self-comparison, right? And then how did they do the crossover design? They got almost 700 drivers who had cellular telephones and were involved in a motor vehicle collision. So this is case periods. So every single one were involved in a traffic accident. Each person's telephone calls on the day of the collision and during the previous week were analyzed through the use of detailed billing records from the telephone company, right? So it's exactly the same thing. It does for exactly the same person, but just compared to something happened before. It could be 1 week or 1 week before. So no argument about that day is a Monday and that day is a Sunday, something like that. So Monday, 1 week before will be a Sunday, a Monday. Okay, the results, the RR for using a cell phone is as high as 4.3, so high, for exactly the same person. But when someone is using a mobile phone, then it's more than 4 times the higher risk. And the units that allow the hands to be free is even higher, 5.9. So if you use the hand-free, the hanger put in your car is even more dangerous. So it's not about holding your phone or not. It's about the distraction from the call or when you're calling someone. For the handheld units, it's also 4, very high. Okay, so the use of cellular telephone in motor vehicles is associated with the quadrupling, about 4 times, of the risk of a collision during the brief time interval involving a call. So this is not possibly done by any other study design, right? So it's a typical cohort study, a case control study, but it's very, very useful to identify the very short period of time for the relationship between cell phone call and risk of the traffic accidents. Personal insight. Mechanisms of selection bias are different between the case control study and the cohort studies. Okay, it's about the mechanism. Why it happens? Why selection bias happened differently in the case control study and cohort study? That's because the mechanism is different. And the choice of study design generally depends on the characteristics of the study setting, like the mobile story, and the outcome of interest in hypothesis. So now you have learned the 2 typical observational study design, right? How can we make that decision? It really depends on the characteristic of study setting, or if it exists in the records or data set. And also it depends on the characteristic of the outcome of interest. Okay. And avoiding the occurrence of selection bias is the best policy because it's very hard to assess the direction, and also it's very hard to do anything about it. So the best way is to avoid it in the process of study design or collecting data. Read my lips. Maintain hands-on method is the origin of confounding control by modeling because it's only applicable for categorical variable, right? But if we expand the idea by chopping them into many small 2x2 tables, then that's the origin of the modeling method development. So it's very important to know the essential or the basic structure or the process to do it. And make sure the cells of 2x2 table it's been erased. The A, B, C, and D, you have to make sure that it's been put in the right position before you can perform a correct estimation of odds ratio, AD over VC. Okay, and always keep in mind the difference between selection bias and confounding. I know it's confusing. It's very difficult, even for a PhD in epidemiology. Believe me, a lot of people still get confused about confounding versus selection bias. But with my help with that table for comparison, it'll be much clearer. Okay. Thank you.